In this video, I'd like to state the fundamental theorem of calculus, and I'll refer to it as part one. We're going to cover both parts in this lecture, and you will not be responsible for identifying one of them as part one or part two. And I'll also start to use the shorthand FTC when I refer to fundamental theorem of calculus. So I'd like to state it, and then I'd also like to provide the proof of the theorem. So just for the statement, what we'll say here is that if f is continuous on an interval from a to b, and capital F is any antiderivative of lowercase f. And just as a reminder, when I say that that is an antiderivative, that means if you were to take the derivative of capital F, you should get lowercase f. So if these hold, then the conclusion is that the integral from a to b of f of x is equal to capital F of b minus capital F of a. So I'd like to spend a good bit of time really going through the proof of this. So a common misconception is that this is the definition of the definite integral. And of course, we defined that in a previous set of lecture videos. So one thing to consider is if you can think about the application of, say, area under a curve, it is clear why the Riemann sums we looked at last week would approximate that area. And we can also visualize why sending the number of rectangles n to infinity should give us an exact value for that area. Notice that looking at the expression I've written here for the integral, there's not really any intuitive reasoning for why capital F of b minus capital F of a should equal that area under the curve. And so in general, the definition provides us with some kind of visual justification for why those things are true. But what's important here is if I can prove that this statement is true based off of my definition, then this becomes another valid way of computing the integral. And of course, what we'll discover is that often this is a much simpler way of evaluating definite integrals than the method of going through the definition, which we saw last time. So to start with here, what I want to do is I'm looking at what I'm trying to prove here. And in some sense, I want to bring in the way that we defined the definite integral before. So to do so, let's start off by bringing in some of our notation. So let's let delta x equal b minus a over n. And we're going to define x sub k, as we have been already, as a plus k delta x. So if I look at what we're trying to show, we need to show that capital F of b minus capital F of a is equal to the limit as n approaches infinity of the sum from k equals 1 to n of f, lowercase f, of xk star delta x. So to be clear, what I've done so far is I've substituted in exactly what the definition is for our definite integral. So that is step one. And step two is that now I'm going to identify that when I'm writing lowercase f, I can replace that now with the derivative of capital F. So my motivation for doing so is now, at least when I compare the left-hand side and the right-hand side, they both deal with capital F, that function. So I'm starting to make it at least more relatable to what I have on the left-hand side. I also want to pause and kind of make a note about expectations here. So in this course, we are not going to be really going over proof techniques. Consequently, you'll find that you're not responsible for replicating involved proofs like this one. You will sometimes be asked to kind of justify something that might involve a line or two. And what I expect here is not that you foresee the next step in the proof, but rather that as I'm going through this, you can make the connection between one step and the next after I've written it. And if it's not clear, of course, ask, or you can also kind of just pause the video and think about that. But keeping in mind that the goal of this is not necessarily that by any means that I'm going to ask you to prove the fundamental theorem of calculus on a blank sheet of paper. So what can I do next? We now have related those two sides, and I want to bring in the mean value theorem, which we covered in our last video. So note that by the mean value theorem, which I'll call MVT for short, there exists some point xk star such that it sits in between my subinterval from xk minus 1 to xk, and that the derivative of capital F at xk star is equal to f of xk minus f of xk minus 1 over xk minus 1, or excuse me, over xk minus xk minus 1. So to pause here, the only thing we needed to assume in order to apply the mean value theorem is that the question at hand is differentiable. So we can assume that about capital F because we're defining it as an antiderivative. And notice that xk star here represents what we called C in our mean value theorem. The only reason I didn't put C here is that we're basically using the mean value theorem on each of our subintervals, each of our n subintervals. And I just wanted to have a way of notating which subinterval I'm in. And it was, of course, handy to use the notation we've already described before. So xk star is some arbitrary point within the indicated subinterval. And I'm now going to set those two sides equal with applying the mean value theorem. Okay, a couple things we can do here is point out that this denominator is exactly how we define delta x. So the distance from xk minus 1 to xk, that's the width of the rectangle. So I can replace that. And the other thing we can observe is that capital F prime is f of xk star, like we saw before. So I can rearrange this to say that f of xk star times delta x is equal to capital F of xk minus capital F of xk minus 1. So I made the observations that I've listed above, and I also multiplied that denominator of delta x over to the left-hand side. Okay, then what I want to do at this point is take this observation and come back up to our goal, which I'm starring up here. That's just, again, where I want to end up. So I want to think about, okay, let's move back to that limit of the sigma notation and try to rewrite it with what I've circled down here. So we're starting with, and I'm going to disregard the limit for the moment, if I start with the sum from k equals 1 to n of f of xk star delta x. So again, that is what I'm looking at here. Now, what I'm going to be able to say is that that is equivalent to the sum of f of xk minus f of xk minus 1. So here using the capital F. Where did that come from? So where did that come from? That's this side, and this is this side. So the only thing I've done here is simply put the sigma notation outside. So I can do this for each of my subintervals. So I'm starting with the left-hand side. If we think about this, this is what we're going to term a telescoping sum, so this will make an appearance later in the course as well. Let's actually write out the terms to see what happens. So when I plug in k equals 1, this gives me f of x1 minus f of x0. The next term, when k is 2, I get f of x2 minus f of x1. When k is 3, we get f of x3 minus f of x2. And essentially, we're going to continue to do this until we hit all n terms. The n minus 1 term would involve f of x n minus 1 minus f of x n minus 2. And then finally, our last term would be f of xn minus f of xn minus 1. But if you think about what's happening here, and this notion of a telescoping sum in general has this, I start to see some cancellation. So there's a positive f of x1 and there's a minus f of x1. There's a positive f of x2 and a minus f of x2. And of course it's buried in my ellipses notation, but there is a positive f of x3 and the next term would have a minus f of x3. And this would continue, so I can observe that I can cancel the f of xn minus 1, but likewise in the ellipses notation, the term just prior to this would have the positive f of xn minus 2. So what's left? We have two terms left. At no point would I cancel the f of x0, which is negatively represented, and likewise there's not a term that would cancel the f of xn. So we're left with, whoops, let's do that, not in red. So we are at this stage left with, put this down here, f of xn, which is positive, and then we have the f of x0, which was negative, so subtracting that there. So this simplified version here is exactly equal to this sigma notation that I had on the right-hand side here. So what we have now is one more observation. If you recall the way that we defined x sub k, x sub 0 is always the leftmost point of my interval, a in this case, and likewise x sub n is always the rightmost point of the interval, b. So where does this leave us? We have that, what I started with on the left-hand side, the sum from k equals 1 to n of little f of xk star is now equal to capital F of B minus capital F of A. And the only thing left to do to make us end up with what is stated in the fundamental theorem of calculus is, again, to come back to this side here and try to think about how I can move from my sigma notation to that integral. That brings in the definition. What I'm missing here is the limit as n goes to infinity. So taking the limit of both sides, this says that the limit as n approaches infinity of my left-hand side should equal the limit as n approaches infinity of my right-hand side. And now we're almost done, because on the left, this is exactly how we define the definite integral of f over the interval from a to b. On the right-hand side, we simply get capital F of b minus capital F of a. And to point out why, notice that my limit here is as n approaches infinity, and these are constant with respect to n, right? This is f, capital F evaluated at the rightmost point would be capital F of b, and this is constant capital F of a evaluated there at the leftmost point. So when I take the limit of a constant, I just get that constant back. So here, we've walked through the steps of proving the fundamental theorem of calculus. Of course, the definition of the definite integral made a big appearance, but also we ended up using the mean value theorem along the way. And the last thing I'll point out here is when we go back to the statement, I've said here that capital F is any antiderivative So keep in mind that if I want to find an antiderivative, let's say of x, right? Most of us would say x squared over 2, but you could also say x squared over 2 plus 3, or x squared over 2 minus 7, right? It's basically any additive constant. But to think about here, if I have two antiderivatives, so suppose, and again, this is the end of the proof, so this is just an aside. If f sub 2 of x is f sub 1 of x plus a constant, the reason it doesn't matter which antiderivative I use is because notice that if you were to take f sub 2 of b minus f sub 2 of a, that's equivalent to f sub 1 of b plus c minus f sub 1 of a plus c. Those constants would cancel, and we get that the difference at these values is the same. So it doesn't matter which antiderivative we use. And conventionally, when people are evaluating this, the additive constant we choose is c equals 0. But I wanted to just point out that language of saying any antiderivative and instead of saying the antiderivative.